Good morning. Hope y'all are doing well today. I was here yesterday. It was just me. So hopefully someone will come today. If not, hopefully you'll watch it later. Yesterday, we kind of introduced the idea of enthalpy, the change in energy with chemical reactions. And there's Kason. Good morning.
Hello.
Glad to see you.
Me too.
All right, so I was just saying, I don't know if you watched yesterday, but we kind of talked about just introducing the idea of enthalpy and what the change in enthalpy looks like in endothermic versus exothermic chemical reactions. So today we're going to go a little bit further and talk about how it relates to the chemical equation, how we can measure it. So there's 3 different ways that you can measure the change in enthalpy of a chemical reaction. And the first method is experimental. So this is a good time to let you guys know that I have an extra credit opportunity for you. I don't know if either of you would be interested in that, but maybe someone else watching would be. So the experiment 13.1, we are not going to do, but I found a video online of someone doing it that's about 6 minutes long, and it's interesting to watch. So I'll post the link, and if you want to do the experiment report for that for extra credit, then that would be an option for you. So that'll just kind of give you a visual how to experimentally determine the change in enthalpy in a chemical reaction. So that's going to be some extra credit. I will post about that. But we're just going to move on for now to page 454. Any questions on that?
Nope.
Okay. So page 454, once you watch the experiment, if you do, you'll understand that it's kind of crazy that chemists have had to do hundreds of thousands of these experiments to get the information that we have today. It's a long process, so it's pretty interesting to think about, but it's good to learn the easier methods. So we are going to, first of all, talk about the method using bond energies. So when a chemical reaction occurs, the valence electrons in these substances have to rearrange themselves in order to make the products. So for example, let's see, at the top of 455, they give you the burning of methane. So they'll show you the Lewis structures there. We're going to bring back Lewis structures this module. So there underneath, you'll see the Lewis structures of first the CH4, which is the methane, and then you'll see 2 O2 molecules. And the valence electrons, the electrons that you see there in the bonds and around the oxygens that aren't bonded, those all have to rearrange themselves in order, they have to break those bonds and then rearrange in order to make the CO2 and the H2O. So as you can guess, energy is required to break bonds and to form new bonds. So let's see, we had to break 4 bonds in the CH4 because you can see the carbon is bonded to 4 different hydrogens. And then the hydrogens will be free to bond to make the water. So let's see, they're just kind of going into detail about that here. So yeah, in order to make the chemical reaction work, you have to break all the bonds in the reactant side. But once the bonds are broken, that's only half of the job because like I said, you have to form new bonds on the product side. So you have to form the double bonds between the carbon and the oxygen, you see those, and you have to form the bonds between the oxygen and the hydrogen in the H2O. So first of all, it takes energy to break the bonds. And then once those are broken, energy is being absorbed by the reactants. And then the new bonds are formed on the product side and energy is released. So each time a bond forms on the product side, the product being formed releases energy. So that's interesting to think about. So to break a bond, energy is absorbed. To form a bond, energy is released. So then we're going to look at kind of the balance between the reactants and the products to see how the change in enthalpy, how to measure that. So this is just kind of an introduction. It might not make much sense yet, but you'll see an example in just a minute. Okay, so I'm going to read you the paragraph at the bottom of 455 because I thought it was helpful to me. So it starts with, for example, suppose a chemical reaction involves reactants with very strong bonds and products with very weak bonds. So your reactant side has really, really strong bonds, so maybe double bonds, triple bonds. Your products have very weak bonds. So since the reactant bonds are strong, it takes a lot of energy to break them. The reactants tend to absorb a lot of energy. On the product side, the bonds are weak, like we said, so maybe that's all single bonds. This means when they are formed, the products release only a small amount of energy. So in this situation, the reactants had to absorb a lot of energy and the products only released a little bit. So when you balance it out, the chemical reaction absorbed more than it released, which means it would be endothermic because it's absorbing energy. So that's kind of how we're going to look at it. Then we'll see a different kind of example. On the other hand, consider a chemical reaction in which the reactants contain weak bonds. So maybe all your reactants have single bonds and your products contain strong bonds. So in this situation, I'm turning the page, 456, the reactants wouldn't need to absorb a lot of energy because their bonds would be really easy to break. But on the other hand, when strong bonds are formed, a lot of energy is released. So in this kind of chemical reaction, it would be exothermic because it's releasing more energy than it's absorbing. So that's kind of how we're going to look at it. We're going to measure the bond strength in the reactants versus the bond strength in the products. So one thing you should see is whether a reaction is exothermic or endothermic. Energy is absorbed and released in all reactions. So you don't have reactions that only release or only absorb. You're always absorbing and releasing energy. It's just determining which is more. Are we absorbing more or releasing more? So that's why we have to measure it. In exothermic, more energy is released. In endothermic, more energy is absorbed. Okay, so moving on, let's kind of look at it. Let's see. If we want to predict whether or not a chemical reaction is exothermic or endothermic, we need to know how strong all the bonds in the reaction are. So we need to figure out how to do that, how to measure that. Chemists can measure the strength of a chemical bond, which is called the bond energy. The process is kind of a lot for this course, so they're not going to tell you how to do it, but they do have a table for you there on page 456. It's table 13.2, and that's a lot of common chemical bond energies that we'll use a lot. One thing I will point out about this table that kind of tripped me up at first is that you have to pay attention to if it's a single bond, a double bond, or a triple bond, because when I did some of my problems, I wasn't paying attention, and I maybe used, if you'll look at the bottom on the left side of the column, or just look at the left side of the column, you'll see the third one down is a carbon bonded to a carbon, and that's a single bond. But if you look farther down, you'll see 1, 2, 3, 4, 5, 6 down, you'll see a carbon bonded to a carbon with a double bond. And then if you'll go 2 more down, you'll see carbon bonded to carbon with a triple bond. Those all have different bond energies because a single bond is going to be weaker than a triple bond. So make sure when you're doing your problems later on that you make sure you look at, is it a single, a double, or a triple bond, because there's multiple ones that are the same that have a different bond strength. So just pay attention to that. Okay, so let's see. Unit-wise, you're going to use the same unit that you use to measure change in enthalpy. So it's kilojoules per mole, and you'll see that in parentheses on your table underneath bond energy. And let's see, the unit could also be kilocalories per mole, or really any energy unit divided by moles. So what does it mean when we apply the measurement of the bond strength? It tells us how much energy is required to break 1 mole of those bonds, or how much energy will be released when 1 mole of these bonds is formed. So For example, if we had 1 mole of Cl2 molecules, we could write the Lewis structure and find out that the 2 chlorine atoms that make up the molecule are held together with 1 single bond, chlorine to chlorine. So if we look at the table, you'll see on the 3rd column near the bottom, it's the second up, chlorine to chlorine, single bond, the bond energy is 240. So that means it takes 240 kilojoules of energy to break 1 chlorine to chlorine single bond. Or if you're forming a chlorine to chlorine single bond, it would release 240 kilojoules of energy. So that's kind of what the information is telling us. So bond energy tells us not only how much energy is required to break bonds, but how much energy is released when those bonds are formed. So it can go either way. So you don't need to memorize this table in any way, but we will use it a lot if you want to mark it. Or the book pointed out that there's an appendix in the back. That's on page 603. It's Appendix A, and it has a lot of the tables all right there in one spot. So if you want to put a bookmark on that page, you can. It might be helpful to you. Okay, so now we're going to have to learn how to determine if an equation, a chemical equation, is exothermic or endothermic based on these bond energies. So first we have to figure out how much energy is absorbed to break the bonds, and then we need to find out how much energy was released when the bonds were formed. And the difference will tell us the change in enthalpy of the reaction. So if you look kind of in the middle of page 457 there, you'll see an equation 13.2, and it's the change in enthalpy is equal to the energy required to break the bonds minus the energy released when the bonds are formed. And if you look at that like an equation, that just means the energy in the reactants minus the energy in the products. And we'll kind of see that here in a minute in a real example. So as long as we know what bonds are breaking and what bonds are forming, all we have to do is use that equation there and the table that they give us. So we are going to look at some Lewis structures now and refresh your memory in case you're a little shaky on it. That was module 4 if you need to go back and kind of refer to that. Okay, so suppose the energy absorbed to break bonds is greater than the energy released when the bonds are formed. In this case, the reaction would be endothermic. And what sign would the change in enthalpy have if it's endothermic? We talked about it yesterday. It would be positive if it's endothermic. On the other hand, if it's exothermic, then your change in enthalpy is going to be negative. So that's just a reminder from yesterday. So if you end up positive, it's endothermic. If your change in enthalpy ends up negative, it's exothermic. And that was also on page 451 in the little table there for you if you need to refer back. Okay, let's look at example 13.2. All right, it says to make ammonia, nitrogen and hydrogen are reacted at high temperatures according to this equation. What is the change in enthalpy for this reaction, and is it endothermic or exothermic? Okay, so the problem requires us to use this table, and we need to know what bonds are being broken and what bonds are forming. So we need to rewrite the chemical equation in Lewis structures. So if you turn the page to 458, at the very top there, you'll see all the Lewis structures drawn out for you, and that's just a little refresher for you because we're going to have to do it on our own in a minute. So make sure you understand each of the Lewis structures, kind of refresh your memory there. There are 3 Lewis structures of H2, because if you'll look back to the equation they gave you, it's N2 plus 3 moles of H2. So they're giving you 3 H2 molecules because that's how many we have in our equation. Okay, and we have to put that many so that we can count all of the bonds. All right, so now the first bond, we're going to start counting the bonds. So the first bond we see is a nitrogen to nitrogen triple bond. And if you look back at your table, it's in the 3rd column about midway down, and it's nitrogen to nitrogen triple bond, and you should see 942 under the bond energy. So we have one of those, and then we have 3 hydrogen to hydrogen single bonds, and you would add those up, and then you have the nitrogen to hydrogen bonds. You have 3 of those on your, no, you have 6 of those on your product side. So then towards the middle of 458, you'll see the change in enthalpy. And here, I'll share the screen so I can kind of write it out. I don't know if everyone's following along. Where did my screen go? Okay, there we go. I'm going to put change in H. So you have 1 mole times 942, because that was the bond strength of your nitrogen to nitrogen triple bond, and that's kilojoules per mole. And that way your moles will cancel and you'll just be left with kilojoules. And you're adding that, it's gonna go to the next line. You're adding that to 3 moles, like we said, of your hydrogen to hydrogen, which was 432 kilojoules per mole. And you're adding that, no, that was it for your reactant side. So we added everything on the reactant side, and now we're going to subtract everything on the product side. So you have a big set of parentheses again, and you have your 6 moles you have your 6 moles of your nitrogen to hydrogen single bonds, and that was 386 kilojoules per mole. And then you would just put that in your calculator, and you would end up with negative 78 kilojoules. So the fact that it's negative tells us that it's exothermic, just like we talked about. And let's see, I'm gonna get out of this for a second. Okay, so a couple of things. Remember the stoichiometric coefficients that you saw in your chemical equation refers to the number of moles. So you always have to refer back to your chemical equation to know how many of each bond you're gonna have. And let's see. I'm just trying to make sure I didn't miss anything else they want to point out. Significant figures, we're adding and subtracting here, so we need to follow the adding and subtracting rules, which means that whatever the least precise place is, that's how we have to answer to. So because the least precise we had was the ones place, that's why we got 78. This isn't about counting how many significant figures, it's about what place is the least significant. Okay, so then moving on, we're going to do one more example before we do some on our own. So we have the complete combustion of methyl alcohol, and they're asking what the change in enthalpy is of this reaction. They don't give us a chemical equation this time, so our first job is to do that. You have to remember what a complete combustion reaction is, and it's just your substance added to O2, and that produces CO2 and H2O. You'll see that there towards the top of 459. And then next we're going to balance it, so then they do that for you. And next you're going to draw the Lewis structures. So first, CH3OH is kind of tricky, but they write it that way because technically they could write CH4O. But they write it that way so that you can see how to make the Lewis structure. So if you see towards the middle of 459, the CH3OH Lewis structure is kind of weird because it's got that one oxygen off to the side. I mean, hydrogen off to the side with the oxygen. But there's that. They drew it out for you. So there's 2 of those because you can see this, the number 2 is in front of that substance in our equation. And then next you have the 3 oxygen molecules, and they drew 3 of those for you. And then they have your little arrow to separate your reactants and your products. And in your products, you have 2 CO2 molecules and 4 H2O molecules. So now we need to count up all of the bonds and look at the bond energies. So first of all, we have 6 C to H bonds in the reactants, and we have 2 C to O bonds, and we have 2 H to O bonds, and then we have 3 oxygen to oxygen double bonds. So they tell you all that towards the bottom. It says on the reactant side. And then on the product side, you're going to count up all those bonds. So you have 4 double carbon to oxygen bonds there. You have 8 oxygen to hydrogen bonds. So then in the end, if you turn the page to 460, they write it all out for you. I'm not going to do that because you can see it there in the book. But the answer ends up being negative 1,286 kilojoules. And because it's negative, that means it's exothermic again. And it says you should already know that because combustion is always exothermic because it's releasing heat. Okay, so 2 things that we need to notice. First, when we referred to the oxygen to hydrogen bonds, the OH, we just use the bond energy for HO because the bonds are independent of the order of the atoms. So it's OH is the same as HO as long as it's still a single bond. And the second thing that they want you to notice is that you're adding all of your reactants bond energies together and subtracting all of your products bond energies together. So don't forget that. That's very important. Okay, so let's do some actual examples. I think that would help you better understand. So we're going to go to 13.2. In your student book on your own. Okay, I'm going to share the screen so we can do this together. All right, carbon tetrachloride is a widely used industrial solvent. What is the change in enthalpy of the formation reaction? And it says, is it exothermic or endothermic? Let me figure out if I can see all of you at the same time. Let's see. It's not letting me. Oh, I just see Hazen, but I guess I can't see Garrett anyway. Garrett, are you with us? He's there, but he's not there. All right. Well, if we want to ask questions, I'll ask Hazen. Okay. So first of all, we need an equation. So step 1 is always going to be.
I'm here, so you can ask too.
Just can't see you. All right. So we're going to write an equation. So first of all, we need to know. They told us it's a formation reaction. Do you remember what a formation reaction is? Have one product or one reactant?
One product.
One product, right. So you're going to form one product with all the individual elements. So they tell us that the product we're forming is carbon tetrachloride. So you need to know how to write that out. So carbon, C, Cl, and it says tetrachloride. Do you remember what tetra is?
4.
Mm-hmm. So it's going to be CCl4, and this should be a subscript, but I can't do that in here. Okay, so this is what we're forming. So let's start with the reactants now. So we're going to have carbon, which is not a diatomic molecule, and we're going to have chlorine, which is a diatomic molecule, so that's going to be Cl2. And I'm just going to put equals, even though that should be an arrow. Is that okay?
Yeah.
Okay. Step 2 is always going to be balance your equation. Okay. So over here we have 1 carbon, over here we have 1 carbon, so we're good there. For the chlorines, we have 2 here and 4 here. So I'm going to add a coefficient of 2 to make this 4 and this 4. So now we're balanced. Step 3 is going to be fun. This is our Lewis structures. Are y'all feeling as rough about these as I was? Had to think back really hard.
I mean, they're pretty easy.
Garrett says. All right. So first we have the carbon then. I wish you guys, I could figure out how to get you guys to be able to draw on here. Let me see if I can try it one more time because that would be super cool. I'm going to give mouse control. It only lets me do Kaysen. Oh, look, there you go, Kaysen. Let's see. All right, Kaysen, are you able to write on it?
That was me.
Oh, okay. So you're able to write on it?
A little bit, yeah.
Awesome. Okay, so draw, if you can, the Lewis structure for carbon.
For carbon.
Mm-hmm.
Oh. Okay. Do you start on the top?
It doesn't matter as long as you use all of the valence electrons. So how many does carbon have? It's in
4.
the 6th column. No, you're right. It's in the 4th column. Sorry.
So it'd be no.
So I think we usually started on the right. So yeah, you do one all around. Good job. All right, so there's carbon. And we're going to add that to 2 Cl2 molecules. So if you want to draw, Kaysen, are you able to draw on my screen?
I think.
Okay, let's let Kaysen see if he can draw 2 Cl2 molecules. Awesome. It's harder than it looks, really.
Yeah. That it?
So these are your chlorine atoms, but what we are looking for here, I'm going to, where did it go? Okay, there it is. Let's see. I'm going to bond them together because they're actually Cl2 molecules. So it's 2 Cls bonded together. So it's going to be a Cl bonded to, let me see if I can move y'all so I can see better. Bonded to another Cl. Now chlorine each has 7 valence electrons. Here's 2, so that means I'm working with 14, right? So I counted for 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 1, and then I have 2 of them. Remember my coefficient was 2 there, right here. So here's another Cl to Cl. This is very tedious. Those are supposed to be dots, just so you know. Okay, so I've got 2 Cl2 molecules. And then I've got my carbon over here. Okay, so that's all we have on the reactant side. So I'm gonna kind of put this in parentheses so y'all can visualize what we're doing here. All of this subtracting, and now I'm gonna draw my Lewis structure for my product, which is CCl4. So carbon's going in the middle here. I've got 4 Cls. Carbon has 4 valence electrons. Chlorines each have 7. So I have 7 times 4 is 28, plus 4 more is 32. So I have to make sure I account for all of them. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so this is our full Lewis structure, and there's no coefficient here, so it's just going to be one of these. So what we're really looking at, number 4, we're going to look at our table that we just talked about on page 456. Excuse me. So number 4, looking at table 13.2. I like to do steps so that I remember how to do each problem. So I'm looking at the table, and I'm going to look here at my Lewis structures to figure out what bonds I'm looking at. So I'm looking at Cl to Cl, single bond, and I'm looking at C here, carbon bonded to Cl. That's all I have here. So I'm looking at carbon to Cl, single bond. Uh-oh, we're running out of time. Okay, we'll wrap it up. So a single bond of chlorine to chlorine, somebody tell me how much that is based on the table. How many kilojoules per mole? Anybody? Chlorine to chlorine?
Would it be 2 Cl2? No. 2 Cl2.
We're just looking at the table to find out the bond energy of one chlorine to chlorine bond. So look at table 13.2.
Oh.
Garrett, you'd be looking for carbon to chlorine.
Carbon to chlorine?
Uh-huh, single bond.
Chlorine to chlorine is 240 kilojoules.
Good. I just want to make sure y'all know how to use that table. All right, Garrett, did you find carbon to chlorine?
What page is it?
456.
$346.
Good. Let's see. No. Carbon
No?
to chlorine.
Oh, carbon to chlorine. I don't see a carbon. Oh, no, I do. 327.
There you go. Okay. So that's kind of what you're looking for. And you can tell here because it's carbon bonded to a chlorine. That's how we know. So we're looking where the bonds are between 2 atoms, okay? So that's what we're looking for. So now we found the 2 that we need because that's the only bonds we have. So step 5 is going to be using our equation. And that's on page 457, equation 13.2. So I just need to fill it in now. So I'm going to have change in enthalpy equal to, and now I'm going to do all of my reactant bonds added together minus all of my product bonds added together. So I have 2 chlorine to chlorine single bonds, and we just found those are 240. So 2 moles times 240 kilojoules per mole. Carbon's not bonded to anything here, so I don't have to worry about that. We're just counting bonds here. So all of that minus, now I'm going to do all of my product bonds. So I have 4 bonds of chlorine to carbon, right? So 4 moles times 327 kilojoules per mole. And I'm gonna put that in the calculator. So you'd have 2 times 240 minus 4 times 327, and forget the parentheses. Did anybody put it in the calculator and get it?
Yes.
What'd you get, Kate?
Negative 830 kilojoules.
Negative 830. Let's see. I got negative 828. But they said you had to do it to the tens place because this one here is reported to the tens place. So that's where you get the negative 830 kilojoules.
Right.
So if it's negative, that means it's endothermic or exothermic.
Exothermic.
Exothermic. Releasing heat, that's negative. Hopefully we will quickly work on 13.3 unless y'all have any questions on 13.2 here.
No.
Okay. If we don't finish 13.3, we'll finish it tomorrow, so don't worry about it. Me off. All right. In an acetylene torch, C2H2 is burned to make the hot blue flame that cuts or welds metal. Assuming that the combustion is complete, what is the change in enthalpy of this reaction? Okay, so I'm going back to step 1, write an equation. So I have to know complete combustion, right? So first I'm going to start with the substance that they give me that's undergoing the combustion. I'm adding it to O2, and that's going to produce CO2 and water. Remember? All right, step 2 is always balance the equation. Okay, so let's see. We have 2 carbons here and 1 carbon here. So I'm going to start, let me just write out my equation, and I'll start adding some coefficients. Okay, so let's add a 2 here to balance out our carbons, and that affects our oxygens. So now I have 4 oxygens here and 1 here. I have 2 here. This is kind of tricky. So that means I have 5 on this side and 2 on this side. So our least common factor is going to be 10. So I'm going to go ahead and put a 5 here to make 10, which means I'm going to want 10 on this side. I already have 4 here. So I can do, let's see. Sorry, I might be making this more complicated for you guys. We can do the fraction way. I was just trying to be fast. Okay, let's see. Let's do it the fraction way. That'll be easier for you. So if we have 5 over here, 2 over here, we're going to multiply this by 5 over 2. That would give us 5. That means I have to multiply everything by 2 to get rid of that 2 in the denominator, and everything over here by 2. And that's going to cancel that. So now what I'm left with is I factor out this 2 to each thing in the parentheses, factor out this 2 to each thing in the parentheses. So I have 2C2H2 plus 5O2, and that produces 4CO2 plus 2H2O. And I think it's probably going to cut me off in a second. Step 3, you're going to start drawing your Lewis structures now that you have a balanced equation. Okay. So I will start with the first thing we're given, which is C2H2, and I have 2 of those. So I'm going to put my C's in the middle, put a bond there, and they're each bonded to an H. So I'm going to put one hydrogen on each side. We know carbon has 4 and hydrogen has 1. So I have 1, 2, and then, so I have 10 total. So here's 2, 4, 6. I'm going to go 8, 10. And I have 2 of these. Okay, so here's my Lewis structures for the 2 C2H2s. Now we're going to do 5 O2 molecules. So oxygen bonded to oxygen. Oxygen each have 6 valence electrons. So I have 12 to work with. So I have 2, 4, 6,